Okay, that is actually we have the table already. That is it is the same. The table is the same as the fixed end moment as you have learned in structural analysis. But today we will use uh, the the finite element procedure instead. That is maybe the straightforward procedure. That is we use the work done the work done the work done method to derive the equivalent nodal force. Okay, so for today we will uh, determine the equivalent nodal force for the beam element as shown in the figure below. Okay, so according to this this load case, actually we have the table that we can replace it directly by using that table. But before that, I would like to prove it how to replace the distributed load, how to replace the distributed load to be the equivalent nodal force, that is composed of the force and the nodal force and the nodal bending nodal moments and the nodal moments. Okay, so if we if we review on the energy equation, that is pi equal to u plus omega. Okay, for u is the strain energy, okay, u is the strain energy of the system, but omega is the potential energy due to external force. Okay, and omega equal to the negative value of the work done due to external force. After we rearrange the equation, and take the first derivative of pi with respect to the nodal displacement and set it to 0 as the stationary principle, as the stationary potential energy principle, we will obtain the same equation like the direct equilibrium method. That is, we obtain k, metric k d equal to F. Okay, and F is derived by the work done. And after we change the sign to the after we solve the equation, and then it's changed from the left hand side to the right hand side. Okay, so the equations become F, the nodal force can derived by this equation, that is equal to the integration of the shape function transpose multiplied with the distributed load function along dx. Okay, so if we focus on the shape function of the beam, if we focus on beam, this is the beam shape function. For beam shape function, that is the Hamiltonian interpolation, we will see that the shape function is composed of 4 equations like this. Okay, so according to this, and n transpose, actually n metric n is right in this form: n1, n2, n3, and n4. Okay, so that means that n transpose is written in this form: n1, n2, n3, and n4. Okay, so after you apply this equation, so what does it mean? It means that the matrix n transpose is the 4 by 1 matrix. Okay, it's 4 by 1 matrix. So it means that the force vector is equal to 4 by 1 matrix also. Okay, so let's be talking about the distributed load. Distributed load first, and we have to uh, understand the sign convention. Okay, according to the sign convention, we know that the positive sign convention for distributed load is like this. Okay, this is a positive sign convention. This means that the distributed load upward is a positive. Okay, and for the nodal force, the positive sign convention is like this also. Okay, so that is M2. Okay, that is the for equivalent nodal force. This is a positive one. So let's we prove with the distributed load first. If we're talking about the distributed load, that is the uniform load. For the case that the load is uniform distributed, okay, this means that Wx is equal to the constant W, right? Is equal to the constant W. And so if we would like to transform it to be the equivalent nodal force, that is F1, F2, and M1 and M2. Okay, how can we do it? Okay, so according to this, we starting with the energy equation, the work done equation, that is the force vector equal to integrate from 0 to L, that is N transpose W. For this case, W is the uniform load, that is the constant, W dx. So what does it mean? It means that F1, we obtain 4 equation, right? It is 4 by 1. So this is 4 by 1 also. So F1 is equal to what? F1 is equal to integrate 0 to L N1 W dx. So what is this? N1 is, when we substitute N1 that is equal to this. Okay. So we obtain what? We obtain it is equal to W over L cube and 2x square minus 3x square L plus L cube, okay, dx. So it is a polynomial function, so it's easy to integrate, right? W and L are constant, so it's become W over L cube, and then we integrate it, we obtain 2x power 4 over 4 minus 3x power 3 over 3L plus XL cube. Okay. So the limit of integration is from 0 to L, right? Okay. So according to this, we obtain that F1 is equal to what? Is equal to W over L cube. And it should be L power 4 over 2, right? Minus L power 4 plus L power 4. So what is it? So it means that F1 equal to WL over 2, right? Okay. And we got it, the positive one. The positive one, that means that the direction is upward because the load, we use the positive sign convention. Okay. So for next, that is F2. For this case, it may be represented by M2, M1. Oh, sorry. The force vector in the second element, that is M1. Okay, I have to write the notation first. The force vector F we may define is to be F1, M1, F2, M2. That is related with the degree of freedom, right? So M1 is equal to what? M1 is equal to integrate 0 to L into, right? W dx. So what is it? Again, from 0 to L, it's become W over L cubed, and then x power 4 over 4 L minus 2x power 3 over 3 L square plus x square over 2 L power 3. Okay. Oh, sorry. This is the final integration. After we integrate N2 is equal to this. Okay, substitute N2 into this equation. Okay, and after we integrate, we obtain this. And the limit of integration is from 0 to L. And after we substitute the limit of integration, we obtain WL square over 12. Okay, this is M1. And it is a positive. What does it mean positive? Positive is mean that it's going in this direction, right? Same as the positive sign convention. So let's move on F2. F2 is what? F2 is integrate 0 to L N3 W dx. Okay. And is equal to what? After we substitute N3 is equal to what? N3 is over here. Okay. Substitute the shape function N3 into this equation. And then we obtain W over L cubed. After we integrate the shape function number 3, we obtain minus 2x power 4 over 4 plus 3x cubed over 3L. Okay, and the limit of integration is from 0 to L, right? So what does it mean? It means that it's equal to WL. Okay. Oh, yes. Okay. So it's equal to WL over 2. That is minus 1 over 2, right? Plus 1. And it's become WL over 2. Okay. So it's positive. So it means that the direction is upward. Okay. Same as we set up the positive sign convention, but you have to mention that the distributed load is upward as a positive also. Okay. So then for the last one that is m2. M2 that is what? That is integrate 0 to L n4, right? W dx. Okay, but n4 is equal to what? n4 we obtain this. Substitute into the equation. So after we integrate, we obtain W over L cube is equal to x power 4 over 4 L minus x power 3 over 3 L square. Okay, limit of integration from 0 to L. So what's happened? Now M2 is become the negative value. That is minus W L square over 12. Okay, what does it mean negative value? The directions of M2 is clockwise instead. Okay, so according to this, we can conclude that the distributed load, that is the uniform load, can be replaced to the equivalent nodal force F1 equal to WL over 2. Okay, and F2 equal to WL over 2 also. For moment, M1 is equal to WL square over 12. Okay, M2 is in this direction, is equal to minus WL over 12. Okay, because it is in opposite direction. Okay, so the direction is clockwise instead. If we compare with the table, from the table you see that if we consider the distributed load, okay, but this case is the downward, right? The distributed load is downward, so F1y is become the negative value, right? It's become the negative 1. Okay, and for M1 also, M1 is a negative instead. F2 is negative minus WL over 2. But M2 is become positive instead. Okay. Now we will move on the next distributed load. That is the linear. For example, if we consider the linear load. For the case that something like this. For the load with length, for the element with length L, and the load, distributed load, is the linear. It's distributed along the beam, along the length of the beam with a linear function. And at the maximum value, it is W, right? So according to this, the distributed load function Wx is equal to what? It is equal to W x over L, right? It is the linear function. So we do the same thing. To find the equivalent nodal force. It is very straightforward. Okay, so the equivalent nodal force is equal to what? Is equal to integrate 0 to L n transpose Wx dx. Okay, if we work out for the linear distributed load, we have F1 equal to what? it will become, because the distributed load is Wx over L. Okay, so for the shape function f1 is integrate 0 to L. Shape function f1 is equal to what? 1 over L cube to x cube minus 3x square L plus L cube. Okay, and multiply with Wx over L. Okay, so for this, we found that W, that is maybe for this case it is a constant. So it's become W over L fold. Okay, and we integrate the polynomial function. We obtain 2x power 5 over 5. Okay, minus 3x power 4 over 4 L plus L cube x square, okay, over 2. Integrate from 0 to L. So what happened? After we integrate it, we found that it's equal to WL. Okay, 2 over 5 minus 3 over 4 plus 1 over 2. Okay, so it's become 3 over 20 WL. Okay, so for equivalent nodal force, we obtain that F1 is F1 is 3 over 20 WL. It's positive. Okay, so we do next with F2, sorry, with M1. For M1, do the same thing. We do the same thing, but we change it to N2, right? That is integrate 0 to L. Okay, 1 over L cube. The integration term is x cube L minus 2x square L square plus xl over 3. Okay, multiply with Wx over L dx. After we integrate, we obtain that is equal to W over L fourth. Okay, and x power 5 over 5 L. Okay, minus 2x power 4 L square over 4 plus x power 3 over 3 L over 3. Okay, so the limit of integration is from 0 to L. Okay, after that, we found that it's become WL square. Okay, and 1/5 minus a half plus 1/3. Okay, so it's become WL square over 20. Oh, sorry, over 30. So positive is mean that positive is mean that it is counterclockwise. Okay, so for this it is upward. Okay, so according to this we obtain M1 equal to WL square over 30. It's positive one. Okay, for F2, okay, For F2 is do the same thing, but with the shape function number 3. With the shape function number 3, that is integrate 0 to L in 3, right? And with Wx over L dx. Okay, after that, we obtain W over L4 and minus 2x power 5 over 5 plus 3x power 4 over 4L. Okay, and limit of integration from 0 to L. After that, we obtain WL. Okay, apply with minus 2 over 5 plus 3 over 4 and is equal to 7 WL over 20 is positive. So F2 is become 7 WL over 20. Okay, and also for M2. For M2, what is it? For M2 is integrate 0 to L N4 Wx over L dx. So what is it? So after we integrate, we obtain that is equal to W over L4 x power 5 over 5L minus x power 4 over 4L square. Okay, limit of integration from 0 to L and is equal to WL square 1 over 5 minus 1 over 4. So it's become minus WL square over 20. Okay, the negative one is mean that it is the clockwise WL square over 20. Okay, actually it is a negative one. Okay, so if the distributed load is downward direction, so we have to change the directions of F1, F2, and M1, M2 also. Okay, so that's all. After we prove for the distributed load for the main case of the distributed load. If we do the same thing with another case of the distributed load, for the case that the distributed load is maybe not the linear or the uniform anymore, it may be another function. It may be another function. We will do the same thing, but we just have the function. We do the same thing, just substitute into the equation of work done. Okay, and integrate along the with the shape function over the length L. Okay, you will obtain the nodal equivalent nodal force. That is the same procedure. Okay, so we come back to after we derive it already. Okay, if we consider for the point load, okay, for the point load we will apply with the fixed end moments that we already know from the structural analysis. And for this case, we can conclude that for the basics or for the general case of load that's normally applied to the structure, the text is already derived for us. Okay, so for example, if the beam element subject to the point load at midspan, the equivalent nodal force, okay, it should be minus P over 2. For this case, the force P is downward, so it means that it is negative value. Okay, so the negative value of F1y is mean that the direction of apply nodal force should be downward also. Okay, and for M1 minus P over 8. So what does it mean? It means that the negative sign is mean that it should be clockwise. Okay, and for F2 negative is mean downward. Okay, but for M2 is positive is counterclockwise. Okay, that's all for the equivalent nodal force. Okay, and then okay, we will have a break a little bit, and then we will come back to the problem that we will solve.